So let's look at lens equation. So they are equations that are used in the calculation of the focal length of the lens, the image distance, the object distance, the magnification of the image formed and all that. So we are coming to look at these equations, how they are related and how they are applied to find these quantities of the lens. So let's delve into it. So the lens equation is a relation used to determine the focal length of a lens or a mirror when the object and image distances are known. So we can use the lens equation when we know the object distance and image distance to determine the focal length of a lens or a mirror. So the lens equation is also applied to the mirror. So with the image and object height known as well, we can determine the focal point since height and objects are related. So there's a relation between the image and object height and image and object distances. And we can also use these relations to find the focal point of a lens if we know these quantities. So the equation therefore is 1 over f equals 1 over di plus 1 over d naught. 1 over f equals 1 over di plus 1 over d naught, where f is the focal length of the lens and it is negative for diverging lenses and mirrors. So f is negative for diverging lenses and mirrors. And di is the image distance, and it's also negative when the image is behind the lens. It's also negative when the image is behind the lens. So particularly, the image distance is negative for diverging lens. It is also negative for diverging lens because almost all the images formed by diverging lenses are behind the lens. They are behind the lens. And d naught is the object distance. So we have to take note of these when to apply them and how to use them to determine the focal length of the lens or a mirror. So this equation relates the object and image distance to the focal length. And the focal length is half the radius of curvature of the lens or a mirror. So if we take the radius of curvature of the lens, which is the point C. So if you take a circle, the center of the circle is the radius of curvature. If you take a curve of the circle, that gives the radius of curvature. So we've done that in our previous video. So therefore, focal length f is equal to r over 2, where r is our radius of curvature. Now, magnification of a lens refers to how much larger or smaller an image appears compared to the actual object. So after an image is formed when an object is placed in front of a mirror or a lens, we therefore compare the image size to the object size or the image height to the object height. So the difference in this gives the magnification of the image, Therefore, magnification is equal to image height over object height or minus image distance over object distance. This gives the magnification of the image. Now, h naught is the object height, hi is the image height. And if the height is negative, the image is inverted. If the height is negative, it means the image is inverted. And if magnification is also negative, it means the image is also inverted. So when we have an inverted image, then it means the height will be negative and the magnification will be negative as well. So if we look at this diagram, we can see the lens, which is a convex lens. So you can see how the convex lens is shaped. So we have R1 to be our outer radius and R2 to be our inner radius of curvature. So this relation, 1 over f is equal to, into bracket n minus 1, into bracket 1 over R1 minus 1 over R2. It is termed as the lens maker's equation. It is used to determine the inner and outer radius of curvatures of the lens. So R1 is for inner radius and R2 is for outer radius, respectively. Then it is mostly used to determine the focal point of a lens when it is submerged into a medium. Specifically, we consider a fluid. So if the fluid, we submerge the lens into the fluid other than air. So we don't consider air in this part. So if you submit the lens into a fluid, let's say water, we therefore use this equation to find the focal length of the lens in that water when light passes through it. Since we know the refractive index of the material and the refractive index of the lens as well, we can therefore find the focal point of the lens in that fluid. So now let's look at some tutorial questions and applications of lens and how to apply the equations that we've talked of. So the first question is, a small candle is 38 centimeters from a concave mirror, having radius of curvature of 24 centimeters. What is therefore the focal length of the mirror? Where will the image of the candle be located? And will the image be upright or inverted? So now let's look at how we will solve this problem. So into our solution, we first state the lens equation, which is 1 over f is equal to 1 over di plus 1 over d naught. So we state the quantities given in the question, which is object distance, which equals 38 centimeters, and radius of curvature, which is 24 centimeters. Now the question is asking of the focal length of the mirror. That's the first question. It is asking of the focal length of the mirror. So we are looking for f. So therefore, our f is equal to r over 2. Our f is equal to r over 2, radius of curvature divided by 2. Therefore, substituting into the equation, we have our f to be 12 centimeters. So the focal length of the concave mirror here is 12 centimeters. Now the next question is asking us to find where the image of the candle will be located. Where the image of the candle will be located, meaning you are supposed to find the image distance from the lens. You are supposed to find the image distance from the lens, which is di. So hence, we are supposed to make di the subject of the equation 1 over f equals 1 over di plus 1 over d naught. So you make di the subject of this equation. So making di the subject of the equation, we are having di to be equal to d naught f over d naught minus f. So after that, we do our substitution. We know our object distance to be 38 centimeters. We input that. We know our focal point to be 12 centimeters. We input that. Then we know we do same for the denominator as well. So after computation, we're having the image distance to be 17.54 centimeters. 17.54 centimeters. So this is the distance of the image of the candle from the from the mirror. This is the image of the candle from the mirror. So will the image be upright or inverted? Now we are supposed to find the magnification as well. The magnification will also tell if the image will be upright or inverted. And we know that magnification is equal to minus di over d naught. Since the question didn't give us the height of the object and the image, we are supposed to use the image distance and the object distance. So magnification equals minus di over d naught. And inputting the values we have di to be 17.54 and you have d naught to be 38. Therefore, leaving us magnification to be minus 0.46. Minus 0.46. So having the magnification to be minus means the image would be inverted. Having the magnification to be minus means the image would be inverted. So now another question is, the accommodation limits for a nearsighted person's eye are 18 centimeters and 80 centimeters. When he wears his glasses, he can see far away objects clearly. At what minimum distance is he able to see objects clearly? At what minimum distance is he able to see objects clearly? So a nearsighted person is someone who can see objects that are close to him or her. So far away objects, he can't see unless the eyes are aided. So we have two range of distances at which this person can see objects. That is from the 18.0 to 80.0 centimeters. So now we are supposed to find the minimum distance at which he can see objects clearly. The minimum distance at which he can see objects clearly. So the distances given here are image distance. You're supposed to find object distance. You're supposed to find the minimum object distance. That is what we are looking for. For nearsighted persons, we consider the diverging length. We consider the diverging length since we want them to see far away objects. Since we want them to see far away objects, we consider the diverging length. So into our solution, our formula is 1 over f is equal to 1 over di plus 1 over d naught. And what we have is, so we have two scenarios here. When the image is at 80 centimeters, when the image is at 80 centimeters, it means the object is at infinity. And when the image is at 18 centimeters, then it means the object is at x. So now we want point x, which is our minimum object distance. So for the maximum object distance, the image is at 80 centimeters, which is at infinity, meaning the object is at infinity. And the image is formed at 80 centimeters. So we are now asked to find the object at x, which gives the image distance of 18 centimeters. Now the distances of the image are negative because for nearsighted persons, I said earlier, we consider the divergent length and the images are always negative. The image distance are always negative. So therefore, we can use this first scenario to find the focal point of the lens. We can use this first scenario to find the focal point of the lens. So 1 over f is equal to 1 over di, which is minus 80, plus 1 over infinity, which is the object distance. So therefore, our focal point here is equal to minus 80. It is equal to minus 80 centimeters. So that is the focal point of the diverging lens. So now we know the focal point from the first scenario. So we can use the focal point plus second scenario to find the minimum object distance. We can use that to find the minimum object distance. So our focal point is minus 80 and the image distance is minus 18 centimeters. So we're looking for d naught. We're looking for d naught. So making d naught the subject, you're having minus 18 times 80 all over minus 18 plus 80 all over minus 18 plus 80. So after computation, we're having the object distance to be 23.2 centimeters. The object distance to be 23.2 centimeters. So the minimum distance at which this nearsighted person can see object clearly is 23.2 centimeters. It is 23.2 centimeters. Another question is, a dentist wants a small mirror that when 2 centimeters from the tooth will produce a 4 times upright image. So what kind of mirror must be used and what must its radius of curvature be? You're supposed to find the kind of mirror that the dentist will use and the radius of curvature of the mirror. So to our solution, we know that 1 over f is equal to 1 over di plus 1 over d naught. So we know the parameters given in the question, which is the object distance and the magnification, which is the object distance and the magnification. So we can use the magnification equation to find the image distance and hence find the focal point of the mirror and use that to find the radius of curvature of the mirror. Now our focal point here is equal to 1 over f. Our focal length is equal to 1 over f equals 1 over di plus 1 over d naught. So making focal length the subject, you have d naught di over d naught plus di. And we know that magnification is equal to minus di over d naught. It is equal to minus di over d naught. So making di the subject, you have minus times d naught. You have minus m times d naught. So since in the question we don't have the image distance, we rather want to make the image distance in the magnification equation the subject so that we have the object distance, substitute that into the focal point equation so that we can use these two parameters to find the focal point of the mirror. So with that done, we then substitute it into this equation, leaving us with f to be equal to d naught into bracket minus m d naught all over d naught plus minus m d naught. So after this, we can therefore bring the d naught out. We can therefore bring the d naught out so that they can cancel out. So with the numerator, we bring the d naught out, and the denominator we do same for it. So leaving us with f is equal to, into bracket, minus m d naught all over 1 minus m. So this is the equation that will be used to find the focal point of the mirror, since we have the object distance and the magnification in the question. So continuation of the solution, we therefore substitute our values, which is the magnification and the object distance, into the equation we generated. So f is equal to minus 4 times 2 all over 1 minus 4. So after computation, we're having our focal length to be equal to 2.7 centimeters. Having a focal point to be equal to 2.7 centimeters. And we said earlier on that 2 times the focal point gives the radius of curvature. 2 times the focal point gives the radius of curvature. Therefore, our radius of curvature is equal to 5.4 centimeters. Our radius of curvature is equal to 5.4 centimeters. So here are some trial questions that I would like you to try your hands on to get better understanding of the lens equation and how lenses are applied.